Hello everyone, and thank you for joining us today. Welcome to Megger's monthly webinar series. Today's topic is alternative testing techniques for instrument transformers. My name is Jamie Smith, and I'm the digital marketing specialist for Megger North America, and I'll be acting as a moderator for today's presentation and supporting you on any technical issues or questions for our presenter. All right, our presenter today is Diego Rabolino, and he's a Megger principal engineer. Okay, let's go ahead and get started today. Thank you for joining us today, Diego.
Good morning, Jamie, and good morning, everyone. Today we'll be talking about alternative testing techniques for instrument transformers, and our main focus will be current transformers. A little bit about the agenda. We will go into definitions and fundamentals on current transformers, some current transformer applications, metering, revenue, protection, accurate classification according to IEEE and IEC, some field testing practices according to NETA, IEEE and IEC, and the alternative testing techniques that we will discuss in detail. And then finally, we will summarize the ideas of the webinar. So let's start with the application and classification of current transformers. And basically, we have two main standards. We have the IEEE ANSI standard, and we have the European or international standard from IEC. In IEEE C57.13.1, the definition of a current transformer is an instrument transformer that is intended to have its primary winding connected in series with the conductor carrying the current to be measured or controlled. Even though this is a simple definition of a current transformer, the definition that IEC provides now looks more into the real condition of the operation of a current transformer, which is an instrument transformer in which the secondary current, under normal conditions of use, is substantially proportional to the primary current and differs in phase from it by an angle which is approximately zero from an appropriate direction of the connection. It is easy to understand the ideal condition of a CT, or a current transformer. We can clearly see that in the ideal condition, the relation that we have between the current flowing in the primary and the number of turns is equal to the current flowing in the secondary and the number of turns in the secondary winding. But the reality is that our current transformer is not ideal, and we cannot take away from the design, from the construction of our transformer, or from the physics of operation of the current transformer, the magnetizing circuit. And this magnetizing impedance will generate also a current that will flow, and it's the excitation current. That will need to be taken into account. If we look into the vector diagram, the arrow that we look in the reproduction of the primary current with respect to the secondary can clearly be seen in this vector diagram. The electromagnetic force that we look in the vector representation here will be 90 degrees apart from the flux. We need to assume in this case that all the primary current is a sinusoidal signal, and all the current voltages and magnetic fluxes will be sinusoidal. And the performance can be illustrated, as you can see here, with the angle or the phase deviation represented as delta phi in this figure. We need to understand where current transformers are being applied. The application, of course, is to bring the information from a high energy side into a low energy side. So from the high voltage, high current environment in our substation, we need to bring that information down to metering or protection devices or control devices. If we start looking into metering type CTs according to IEEE, there's a high degree of accuracy at the specified standard burden at 10% and 100% of the rated primary current. So what we're looking at is very specific and accurate measurement of current, and the transformation that we have from primary to secondary has to be extremely accurate. When we're talking about revenue metering equipment, there's one requirement. The transformer correction factor, or the TCF of the CT, shall be within the specified limits when the power factor, lagging power factor in this case, of the metered load has any value between 0.6 and 1.0. It is interesting to understand this 0.6 and 1.0 because nowadays, with the latest technology that we have on relay and protection, our power factor is mainly unity. And we need to remember that in the system, we don't have only digital technology, we also have electromechanical relays, and that's the reason why we go into this value between 0.6 and 1.0. As you can see in this table, according to the IEEE, the standard accuracy class for metering CTs is 0.3, 0.6, and 1.0. We have additional classes with higher accuracy, 0.15. But the standard ones listed right now, and the ones that we're going to discuss right here, is 0.3, 0.6, and 1.2. As you can see on the table, we look at the 100% rated current, and the values go 0.3% minimum, maximum. If we go at 10% rated current, the error, the allowable error, is twice that number. So we can see here that for a 0.3 class at 10% rated current, the maximum and minimum error is 0.6%. And you can see the same effect goes for the following accuracy classes. When we're talking about the accuracy classes, one of the interesting things that has been provided in the IEEE standard is the use of parallelograms. So we can see here, based not only on the information of the discrepancy by magnitude, but also the discrepancy by angle, that it should fit the response of the ratio in magnitude and angle within the parallelogram corresponding to the accuracy class. In this case, we can see what is the 0.6 accuracy class, 10% and 100%, and we can see what is the 0.3 accuracy class at 10% limit, 100% limit. According to IEEC C57.13.1, the ratio error on phase displacement at rated frequency shall not exceed the values given in the standard, and the burden can assume any value from 25% all the way up to 100% at the rated output. When we look at the classification, it is interesting to see that for the accuracy class, the IEC standard will identify values between 0.1 and 1. And if you look a little bit into the rated current for the evaluation, you will see that it goes beyond 100%. So it will go from 5% rated current all the way up to 120% rated current. And you see that for the standard classes, 100% and 120% will give you basically the same error, not only in magnitude, but also in phase. There's some special classes according to IEC, which is the 0.2S and 0.5S. And the difference here you can see is that the accuracy remains even at 20% of the rated current. As you can see here, not only for magnitude, but also for the phase deviation. That is the difference. So in the IEC, we see this 0.2S or 0.5S. The standard burdens for metering CT applications, we have the designation will be a B, 0.1, 0.2, 0.5, 0.9, and 1.8. Basically, this is the complex impedance acceptable for the burden to remain under the accuracy specified on the nameplate of that CT. You can see here that basically the complex impedance is given as 0.1 ohm, 0.2, 0.5, 0.9, 1.8 ohms. From here, we can easily estimate the volt amperes or the burden designation, assuming in this case that we're talking about a 5 amp secondary current output on our CT. Typically for North American applications, it would be 5 amp on the secondary. There is some applications with 1 amp, and mainly for the European standardized CTs, those will be with 1 amp on the secondary. As you can see from here, we can derive basically the VA and the power factor for that specific burden. When we talk about current transformer protection and protective relaying, we need to look now into some specific standards dedicated for this application. IEEE C57.13.1 specifies that protection CTs must remain a ratio error no more than plus minus 10% in a range from 1 to 20 times rated secondary current at the specified load. What the standard is trying to say here is that we are not worried about high accuracy on this CT, but we are worried about this CT being able to handle primary currents or overload up to 20 times the rated load on the primary and, of course, on the secondary as well. The classification according to IEEE, we have Class C and Class C. Class C is the one that is mainly used and you may encounter in the field, which is the classification where the leakage flux in the core has a negligible effect on the ratio within the limits of current and burden, and that's why the ratio is calculated. In the other case, when we're talking about Class C, the core and the leakage flux creates a 1% difference between the actual ratio correction and the calculated ratio correction. That's the reason why the ratio in this case is tested. There's an additional classification, which is classification X. And in this X classification, basically there will be some definitions, some agreement between the manufacturer and the end user. And in this case, you can see that you need to define the minimum knee point voltage, the maximum exciting current at the point of knee point voltage, and you need also to define the secondary winding resistance measured and corrected to 75 degrees C. When we're talking about protection CTs, the standard burdens according to IEEE will be 1 ohm, 2 ohms, 4 ohms, and 8 ohms. If we go back to the definition and we define that the protection CT should be able to handle from 1 to 20 times the secondary current or the primary current according to the rated value, you can clearly see here that if we are talking about a secondary current of 5 amps, we can easily define the effect of the burden on the classification. If we go from here, from say 5 amps all the way up to 100 times to 100 amps and 8 ohms, our VA will be represented in the classification that we have here. Our protection class CTs, according to IEC, we can look at the specification, and basically we have class 5B, class 10B, and what you see, the percent error for the nominal primary current is plus minus 1 or plus minus 3. And the error, the compound error limit for the current accuracy will be 5% or 10%. Let's talk now about the testing practices that we have in the field according to reference standards like NETA, IEEE, and IEC. In summary, when we go to the field, we are requested to perform insulation resistance test, winding resistance test, excitation or saturation test, ratio and phase deviation, polarity, and burden test. One of the features that we need to take into account is the demagnetization of the CT after the winding resistance test. So let's go one by one and let's analyze these testing practices. First of all, when we are looking into the NETA standard, you can clearly see here that it's requesting resistance measurements or contact resistance measurement, insulation resistance test, not to exceed 1,000 volts, polarity test, ratio verification test, and excitation test. In addition to that, we need to measure the current circuit burdens at the transformer terminals, perform insulation resistance test on the primary winding and secondary grounded, If possible, withstand test of the primary winding. If possible, power factor or dissipation factor test. And we need to verify that the transformer secondary circuits are grounded according to the standard. Let's start the analysis with the CT insulation resistance test. It's typical practice to perform the insulation resistance test, like it was explained before, at voltages below 1,000 volts. And when we are looking at this here, we need to make sure that we create electrodes by shorting the terminals, in this case H1 to H2, and the other electrode typically will be X1, X2, and ground. There are different parameters and different configurations that can be used to test the insulation resistance. We want to see that your current transformer has the ability to handle the voltages or the voltage level at which it has been classified for. When we talk about winding and lead resistance, we need to understand the reason for doing this test. First of all, we are trying to confirm that the DC resistance of the CT is within specification, and there is no high resistance connection in the CT or the wiring connected to it. When performing the winding resistance test, the temperature needs to be corrected to 75 degrees to be comparable and to do some trending analysis down the road. Why are we doing winding resistance? Because there are different forces in the system. We have static stress, the weight of the connected conductor. We have dynamic stress, wind, seismic activity, vibrations in circuit breaker operation, electrodynamic forces under short circuit conditions. In order to calculate the ratio correction for a Class C CT, we need to consider the internal resistance and external impedance, including the secondary lead resistance. So it is always a good practice also to know the resistance that we have on the CT. After a winding resistance measurement, where we have saturated the core of the current transformer, we need to provide a procedure to demagnetize the core. This procedure is called demagnetization. And basically, to demagnetize the core on any kind of transformer, we have typically three ways. A variable voltage constant frequency source, we have a constant voltage variable frequency source, and we have a decrease in the amplitude of an alternating DC current. So these are basically the three methods that can be used. If we are thinking about our current transformer, and we understand that the secondary is designed for low voltage, it is easier to apply an AC signal to demagnetize from the secondary side the core of this current transformer. That might not be the case for a power transformer. In a power transformer, to be able to reach saturation, as you can see here, if first you need to reach saturation, then you need to apply a voltage that might be beyond the level of the rated voltage designed for that transformer. So it's going to be very complex, very difficult to provide a voltage source, a sinusoidal voltage source, and go up with voltage all the way to the nominal rated voltage, either primary or secondary side. In factories, they will do secondary side. But when we're talking about a CT, in this case, for our CT, the easiest way to go is just applying an RMS sinusoidal voltage. And as soon as we increase and we saturate the core, we start decreasing the magnitude of this voltage all the way back to zero, where we expect to have a zero coercivity and zero remanence point. The excitation and saturation curve after the demagnetization procedure is basically an AC test. What we are doing here is we are increasing the AC voltage applied to the secondary winding of the CT, and we measure simultaneously the current on that secondary winding. What we're trying to do here, we're trying to confirm that the CT is of the correct accuracy rating. The CT has no shorted turns. No wiring or physical short circuits have developed in the primary or secondary windings of the CT after installation. And out of this generic terms, one of the things that you can see as well with excitation saturation curve at the different voltages is if the condition of the insulation in the interwinding, intercurrent insulation is good, because now you are applying voltages that can go from 10 volts all the way up to 2000 volts. So if there's any issue with the insulation, that will be also seen with excitation saturation curve. What are we doing here? Basically, once we get the saturation curve from the field, this will be the measurement that we get from the field. We start looking at the linear response area and the nonlinear or saturated zone of your saturation curve. And when you look at this information, you need to compare those values against those provided by the standard or those provided by the manufacturer or of the CT. Now we move into ratio test. As soon as we know, according to this table, as soon as we know where is my saturation point for the specific CT that I'm testing, I know that ratio test can be measured on the linear zone of the response. So the next stage is ratio test. And the ratio test basically could be done by two methods, the current method and the voltage method. For the current method, you need a variable current source, but it might be a little bit complicated for you to bring an AC source for current going all the way up maybe to 1000 amps or 2000 amps or whatever is the current that you need to run the test on the primary side of that transformer. And on the secondary side, you will need an amp meter to be able to measure the reflected current to the secondary. The other way is to apply just an AC voltage, sinusoidal voltage, and measure the voltage on the primary side. This way, as I was saying before, because you do not expect to have a high voltage secondary side on the CT, you can easily do the test with the voltages with low voltage, and in most of the cases, there is no need for voltages beyond 300 volts AC. That allows you to bring a small unit that's really not heavy unit, and you can perform this test easily in the field. As I was explaining before, one of the advantages that we have from IEEE is the provision of the parallelograms. And you can clearly see that you may get a number for the magnitude, you can get an angle given by the phase deviation, but it's easier just to plot that information in a graph, and you can visualize that in reality, at 100% rated current, your transformer complies with the standard, and same way at 10% rated current, which is the red limit in this graphic, and the 100% is the blue limit in this graphic. And that way, we analyze based on the specifications and the information provided by the standard. It has to comply with the phase deviation values and the magnitude values. For the polarity test, one of the most important things here is not to avoid the test of polarity and make sure that you have clear what the direction of the current flow is in your circuit. If you are in the field and you're working on a protection scheme, if you have inverse direction of the current, you will create a fault in your system, or the fault will be created without a real fault in the system. In the metering environment, just imagine that you are power generation and you're transferring energy from power generation down to transmission. And if you have an inverse polarity on your meter in CT, instead of sending an invoice to transmission, you're going to be sending a check. So it doesn't make really sense, but you need to be clear what is the direction of the flow for you, especially for your protection devices. Be very careful on the direction. So make sure that the polarity is the correct polarity on the installation of your CT. Moreover, when we're looking at the procedure, The last test that is being requested is to carry out a burden test, and not just the simulation of the burden and run the test with a simulated burden, but to measure the real burden which is connected downstream from the secondary winding of my CT. What the intention is here is to determine that the real ohmic load on the secondary side fits within the specification for accuracy of that specific CT. So if you have a CT with a burden classification of 4 ohms, downstream, if you measure that burden, should not exceed those 4 ohms. Make sure that that is happening. And when you do the measurement, you can actually use the measured value of your burden to analyze the ratio error by magnitude and by angle. You can simulate mathematically what will be the deviation at 100%, 50%, 25% of the burden. But most important for you is to know what the real burden, the existing burden is on your system, and apply that number to the estimation or to the measurement of ratio and accuracy. The measurement is quite simple. You just need to connect the test set to the leads going downstream from the CT, and you measure directly the complex impedance of that burden of the system. As you can see here, you will get from the test set the information that you're looking for based on ratio and phase error, the magnitude, depending on the percentage of the rated current, and the phase deviation, depending on the rated current. So let's say you go from 1% rated current all the way up to 200% rated current, and your VA will go 100%, 50%, 25%, whatever the percentages that you need to analyze. And that is by simulation that is performed. So let's talk a little bit about the alternative testing technique. What we have seen so far is what we call routine testing, or what is recommended by the standards. But let's see how we can become more efficient without affecting the accuracy of the system. So if you come to the field, one of the problems that you may face is that not all the CTs have the same configuration, and you may encounter a CT with a similar nameplate to what I am showing you right now on the screen. You can see in this case that this current transformer has 2 terminals on the primary side, H1, H2, but it has 5 terminals on the secondary side, going all the way up from X1 to X5. And you also see here that the primary, with respect to secondary, has different current values. So we need to understand what is going on here, and we need to measure one by one. The traditional method was you use your CT test set, and you start looking terminal by terminal between X1 and X2. Then you go X1 and X3, X1 and X4, X1 and X5. And after doing your ratio test, then you go on your winding resistance test, and you start looking again into X1, X2, X1, X3. Then you start doing some insulation resistance test, and then you start doing your saturation test. So there's maybe more than just one piece of equipment. When we were doing this in the traditional, maybe a few years ago, that was the traditional way to do this, just going one by one. But then there's a non-concurrent test. On the non-concurrent test, you can connect all the terminals of your secondary side of your CT. You connect the primary side as well. And based on these, you will be testing one by one each of the sections of your secondary winding on your current transformer. You test the first one, the first section, then you go to the second one, to the third one, to the fourth one. And this will be a one-by-one procedure. Of course, all you can see here takes time. And the idea is to minimize the effort, to minimize the time, and become more efficient. In order to do this, the alternative is to go with a concurrent measurement. This concurrent measurement will inject a voltage on the full secondary winding of the multi-tap CT. In this case, we're talking about an X1 to X5 secondary winding. You can clearly see that we keep the connections for all the terminals or all the taps on the secondary winding. We keep the connections for all the terminals on the primary winding. And simultaneously, we measure voltage on all the CT secondary taps. At the same time, we are measuring the voltage on the CT primary winding, and we measure the current passing through the CT secondary and the phase angle between primary and secondary. So with all this information in a simultaneous way, and with the ability to have 5 voltmeters to perform concurrent measurements on all and every single tap, we can select the test, and we can select the winding sections or the taps that we are interested on. So in this case, now you have all the combinations of the testing taps like X1 to X2, X1 to X3, X1, X4, X1, X5, but also we have the interwinding options, so X2 to X4, X2 to X5, X3 to X4, every single combination of the secondary taps on that CT. Why do we need this? If for whatever reason you decided that the original installation will work with your CT connected from, say, X1 to X5, and down the road you need to change that to a different configuration on your CT, and you want to go from X3 to X5, you need to know what the condition is of that tap. You need to know that everything fits within the accuracy and within the specifications that you're looking at. So you can have in one selection all the saturation tests, all the ratio tests, and all the winding resistance tests. You can also select the insulation resistance test, and with one click here, you will be able to run in a simultaneous concurrent method all those tests. To give you an idea, as soon as you have selected this, you will go on the procedure. The first test that you will do will be the insulation resistance test. Then you will go into winding resistance test. After winding resistance test, automatically the test set will be able to demagnetize, applying an AC signal or a DC signal, because that's something that you can configure in the settings of the instrument. And from there, you will have the excitation saturation curve. When we're looking at this and having the ability of 5 voltmeters in the system, we can simultaneously measure all the values of the saturation curves on every configuration, and also the interwinding configuration. We can look at all the need points, ratio, polarity, and winding resistance on all taps. So in summary, this concurrent measurement on all the taps in a simultaneous measurement process is really a way to reduce the testing time. When we talk about this concurrent measurement, we see that we have several data points that are being measured as voltage is applied to the CT secondary, and we increase the voltage to saturate the CT. The ratio is being calculated in the same way as the ratio of voltages between X1, X5, H1, H2, and the calculation is based for the other interwinding systems based on the relation that we have of voltages between primary and secondary. The saturation curve is plotted between X1 and X5, and the interwindings are being calculated and plotted at the same time. You can clearly see here on this example that when we use the concurrent method, you can get the saturation current, the saturation voltage and current numbers in a tabulated manner, in a tabulated way. And represented in this table, you will have every single subsection of your CT. Let's look a little bit into the process. So we were saying the first test that we will be performing is the insulation resistance test. As you can see here, the ranges for insulation resistance test will go up to 1 kV, and you can select this either 500 volts or 1 kV. Then, when you look into the winding resistance test, if you look at this example, when I look into X1, X2, and the value that I obtained for X2, X5, the sum of those two values corresponds to the total value between X1 and X5. And we understand that these are just resistances in series, so it's basically an addition of values. It's interesting to say that during the process that we have done for the validation of the concurrent method and the non-concurrent methods were compared. As you can see here, for the winding resistance test, a comparative analysis between concurrent measurements and non-concurrent measurements was carried out, and we see that the differences are really minimal and negligible. On the saturation test, again, you can clearly see here that we see the response of all the taps and all the sections of the secondary of our CT, from X1 all the way up to X5, including all the interwinding measurements. One of the things that we have to remember as well is that the way that ANSI IEEE defines the knee point is based on the tangents of 45 degrees intersecting the saturation curve. So basically what we have here, we have voltage on this axis and we have current on the x-axis. And basically what we have here is the derivative of voltage with respect to the derivative of current, and this should be equal to the tangents of 45 degrees. Based on that analysis, we define where the knee point of the curve is. As you can see here, these are the saturation test results. Again, a comparative chart between concurrent measurements and non-concurrent measurements. The differences are negligible. Ratio and polarity test. As you can see here, the accuracy, the ratio is being calculated in magnitude and phase deviation. One of the things that you need to see is that the phase deviation is 0 degrees or very close to 0 degrees. So 359 degrees and 59 minutes is okay. And the polarity is correct. Again, just a comparative analysis between concurrent and non-concurrent measurements, and the differences are negligible. Coming out from the testing procedures, we need to consider certain issues that we have encountered and you as end users will encounter in the field during saturation of protection class CTs. If you are in the field and you find a C800 classification CT, you understand that the minimum voltage that you require to bring this CT into saturation might be 400 volts AC, but there are specific designs where the saturation voltage will exceed the 800 volts and might be 1300, might be 1500 volts to achieve a 1 amp of excitation current. There's more CTs, especially on the transmission side, where these transient type CTs will reach a saturation voltage sometimes 3,000 volts, 4,000 volts, or even higher. And it will be very difficult to achieve saturation at 1 amp. What this means is that if you are in the field and the typical instrument which provides you an output of 2,000 volts or 1 amp will not be able to reach saturation on these CTs, and you will not be able to get the saturation curve for this unit. So what has been done? One of the things that has been done is, of course, to change frequency. You apply the sinusoidal signal, but you start changing the frequency. You start bringing down the value of frequency. And as you can see here, if this is the saturation curve for 60 hertz, then this is the saturation curve for 50 hertz, and this is the saturation curve for 45 hertz. So the lower the frequency, the lower the voltage that you will need to reach saturation. Based on this concept, One of the proposed methods and the alternative to be able to measure saturation and obtain the real saturation curve on this type of CTs on the protection side is the DC method. And this is an alternative method to obtain saturation and excitation curves of the CT with very low DC voltage. This method completely eliminates the need for dangerous high voltages during testing. As I was saying, if you're using AC, you will need to crank up the voltage to maybe 4,000 volts, maybe even higher voltages than that. And the reference that we get from IEC, it says that this is the most suitable procedure for the determination of the saturation flux. If we look into this alternative method for saturation, basically you can clearly see on this diagram that by applying a DC signal, we are looking into the integration of the voltage as a function of time, and that be reflected as a flux as a function of time. And we will look into the saturation curve, voltage time versus excitation curve. To be said in other words, in an arbitrary voltage as a function of time, this voltage is applied to the secondary terminals, and the flux as a function of time that is linked through the secondary winding at time t is related to this voltage according to the equation below. After the completion of the test, one of the things that you have to be careful about is reporting. Make sure that on your report, on the final report that you're providing to your customer or for you as an end user, you have a complete nameplate information. When you fill out the information of the nameplate, you define the class, the accuracy. You define if this is an ANSI standard CT or if this is an IEC standard CT. And the test set will configure itself to be able to test the unit according to that specific standard, either ANSI or IEC. So you have the nameplate information, then you have your saturation curves, you have your ratio and the polarity, you have your burden test values, those measured and those that are calculated or estimated based on percentages. And then you have your winding resistance and your insulation resistance. All this information should be in your report. When we talk about the recommended testing sequence, so basically we're saying you started the routine test and now you provide the nameplate information. As soon as you provided the nameplate information, you're ready to start the process. And you start with an insulation resistance test. Then you do winding resistance test. You demagnetize the core. After demagnetization of the core, you go with excitation saturation test. And finally, you will do your turn ratio and polarity test. All these tests that we have here now can be done in the concurrent method. And this is the balance between efficiency, your time, your money, the resources that you're spending in the field. Now you can do, for example, a protection CT will be tested with all these procedures, having all the concurrent methods in about 7 to 10 minutes. Now you know the excitation and saturation test typically is done with AC, but if the saturation knee point goes beyond 2,000 volts, the easiest way to go is with DC. So now those two technologies are available, having this alternative technology, which is the DC application. Finally, you record all the information, you generate your test report, and your testing process is complete. Bear in mind that lack of testing and on-time maintenance may derive into things like this. And this is exactly what you do not want to see in your substation, in your facilities. Let's talk now about the MRCT, our Instrument Transformer Test Set by Megger. In this device, we have AC and DC saturation. This alternative DC technique for saturation excitation testing, as it has been discussed during this presentation, will allow us to do AC saturation all the way up to 2 kV and DC saturation all the way up to 30 kV. As you can see in this example, This is a CT tested in the field with a saturation knee point at about 20,000 volts. The demagnetization, it's not just a procedure. What is interesting here is that we are providing as well the as found values and the as left values. So before we start the process, you want to know how much remnant saturation you have on your, or remnant magnetization you have on your CT core. And after the demagnetization process, what is the remnant saturation or magnetization of the CT? So that information is also being provided. One of the problems that you may encounter is that you go and you try to test a piece of equipment in the field, and the information on the nameplate is not readable. You may try to get some drawings, you may try to get some information from engineering, or that information might not be available. So the only thing that you have in this case is to use a device like the MRCT and apply the nameplate guessing functionality. This way, you can predict the nameplate ratio, the accuracy class, and the VA rating for burn. Some other features that we have on the MRCT, we have the lead connection checking algorithm, which allows you to check for proper connection prior to test beginning. It will monitor the voltage and current during the test, and will give you a warning signal if unexpected results come up. One more thing, and this is typically, you will go to the substation, you are doing your test. Let's say that you're talking about a BCT, a bushing CT, and this CT is mounted on any other piece of equipment. You can say a power transformer or a super breaker. And the only thing that has been isolated, that has been de-energized for your testing, is that transformer or that super breaker. Everything else in your substation is energized. So you cannot control the noise from the substation. One of the big challenges that we have to face is to overcome the effect of this noise. And now, necessary filters and filtering algorithms have been implemented in the MRCT to minimize the effect and be able to test even BCTs on reactors in 765 kV yards. The MRCT basically is providing as well with a CT assessment at the end, based on the results that you have gathered from all the testing procedures. You will get an assessment of the condition of that CT according to the standard it was tested against. In summary, the electric condition assessment allows validation of nameplate information, reliable and safe operation coordination. The concurrent method for electric testing improves testing time and maximizes the efficiency of the field testing practices. A protection CT with 5 taps on the secondary can be tested now in a time between 7 and 10 minutes. Protection class CTs may require high voltage applied to the secondary winding to reach saturation, and the alternative method to obtain the saturation curves of a CT, as it has been discussed during this webinar, is based on DC voltage, which will reduce the risk or exposure to high voltage and minimize the size and weight of the instrumentation required. Reporting is paramount. Results should comply with the reference standard requirements. So keep this in mind. I hope that the information that has been provided today is useful for you, and will give you some ideas on how better do your testing, which way you could be more efficient in your testing procedures without affecting the accuracy of your testing. Thank you very much for your attention. Jamie?
Okay, thank you, Diego. At this time, the presentation portion of the webinar is officially concluded. I just want to thank you all for attending. Also, we hope to see you again at our next webinar on October 20th at 10 a.m. Central Standard Time. And that webinar is titled An Insight into Differential Protection Scheme for Different Applications. And that's going to be presented by Vijay Sundaram, one of our Megger applications engineers. All right, thank you again, and have a great weekend, and please remember to answer the survey.